Now looking at the next section, Chapter 8, Section 3, we're starting the new shape hyperbolas. And you'll see a lot of formulas look very similar to what we did with an ellipse, but there will be some very minor differences that I will try to emphasize. Starting with the definition, this one sounds close to what we had for an ellipse, but instead of it being the set of all points whose distances have a constant sum, now it's a constant difference. So the idea is that now if you pick a point somewhere on this shape, the hyperbola, and if you do the distance from one focus and subtract the distance from the other focus, you will get the same answer no matter which point you pick. So if the difference from here to here is 3, then if I pick another point like over here, you'll get that same answer of 3 when you extend to the two foci. Other than that, we still have an a, a b, a c, an h, and a k value. The coordinate of the center is still hk. We do have a different term that we associate with the a variable, but it's a very similar idea. So for the hyperbola, a is the distance from the center to the transverse axis endpoint, which is also sometimes called a vertex or the vertices, like in this graph. But they will often use the term transverse axis endpoints, and that's how you'll know that you're dealing with the hyperbola just based on that term alone. So make sure you associate transverse axis endpoint with A. And then for the B value, it's not shown on the graph here, but for B, there's another point that goes up, and that value is the conjugate axis endpoint. I'll show you what the B values do in a little bit. Basically, we'll create an imaginary box based on A and B, and then we'll use those dimensions for the rectangle to guide the shape of the hyperbola itself. So it's not directly on the image, but there is a B value that's guiding the shape of the hyperbola. And then C, just like with the last shape, is the distance from the center to the focus. And it doesn't matter which focus you pick. Either way, the center is going to have the same distance from there to a focus. And just like with the last shape, the ellipse, A and C will always go in the same X or Y direction. In this problem, I'm showing you a left to right hyperbola. So A and C are going left and right, or the X direction. But you could also have one that's extending up and down, in which case both the A values and the C values would be extending in the vertical direction. So they will always go in the same X or Y direction. Here are the two standard forms for a hyperbola, and you'll notice that this also looks very similar to the one for an ellipse. The only thing that has changed in particular is that now it's a minus sign instead of a plus sign, and that comes back to the definition we just looked at. This one has a constant difference to the focus, while as the ellipse had a constant sum. So we had a plus sign in between the x and the y fractions. Well, we still have an h and a k, and those are still the numbers touching x and y, so this should still be pretty easy to identify. H, k will be the center of the ellipse. We do have a different rule for distinguishing between a squared and b squared this time. Since we have one positive fraction and one negative fraction, our order will be more important. The one that we write first will always be the a squared value. It should be the positive one. If you have the negative one first, then you want to flip the order around. So a squared is always the first denominator. It should be that positive denominator. Whether it's underneath x or y will change though. If it's underneath x, that's how we'll know that it's a left and right hyperbola. If it's y that comes first, if it's a underneath y, then that's how we'll know it's an up and down hyperbola. So when you were asked to find the vertices from the equation, look at what a was underneath. If a was underneath the x variable, then you're going to add and subtract a from the x coordinate. And this is the exact same process we had for an ellipse. It's just we're applying it to a different standard form. For finding the foci, we still look at what a is underneath. If it's underneath x or y, we add and subtract from the x coordinate, and we're still basing that on the value c. But something I do have to emphasize here, it has changed only a tiny little bit. Now the formula says a squared plus b squared equals c squared. For the ellipse, it was a squared minus b squared. So this equation will change based on which shape you use. The way I keep track of it is I always look at the sign, the plus or minus sign from the shape, and I do the opposite sign for the a squared and b squared terms. So since this shape has a minus for the x and the y fractions, do the opposite and add a squared and b squared to get your c squared value. So now we'll look at some examples of finding the center, vertices, and foci. The first thing I always like to do is identify the center, and we are asked to find that in this problem, so it's still important. The number that's being added or subtracted from x in this case is 0. So I'm going to say h equals 0. The number being added or subtracted from y is k. And since I don't see one, that is also 0. And then a squared is always the first denominator. It's not about the bigger one anymore. So in this case, if a squared equals 36, that means a is 6, the square root of the first denominator, and b will always be the second denominator. It should be the negative one. So if you take the square root of 49, that's 7. I will need to find the c value for identifying the foci. So I'm going to do the opposite sign. Since I see a squared and b squared down here, I'm just going to flip this sign and do a squared plus b squared. So 36 plus 49 will equal c squared. So then if I keep solving this, I will have 85 equals c squared. And then to find c, we need to take the square root of this number. So make sure you always try to break down those radicals. And you can use a factor tree to do that. So find two numbers that multiply together to equal 85. For example, 5 times 17. But since 5 and 17 are both prime, this can't break down anymore, which means square root of 85 is as simplified as it gets. So in this case, it's going to be okay to just leave our answer as the square root of 85, but always try to break down the radical. Now that I know h, k, a, b, and c, I can go through and list all of the components they asked me for, starting with the center. This is the easiest one. It's always just the h and the k value. So in this case, my coordinate is 0, 0. Next, I'll go on to the vertices. And the vertices, or the transverse axis endpoints, if they use that term instead, these are always based on the a value. So I know I need to either add or subtract it from the x coordinate or the y coordinate. Which one I add it to will be based on where a came from. Since my a value was underneath the x variable in this case, then I'm going to add and subtract it from the x coordinate. So adding and subtracting 6 from 0 just gives plus or minus 6. Or you can write that out as two different ordered pairs, negative 6, 0, and 6, 0. And then for the foci, I told you that a and c always go in the same direction. So since a is tied to the x variable, since it's going in the x directions, that means c will be as well. So I'm going to start from the center, but add and subtract the square root of 85. So plus or minus square root of 85, comma, 0. And those are all the components for this example. Here's a slightly more complicated example. Now that we have different h and k values, our computations will take a little bit more work. So starting off with the number being added and subtracted from x, that's a positive 1. And the number being added and subtracted from y is a negative 3. A is always the first one. It's not based on the biggest one anymore. So the first denominator, square root of that is 5. And the second denominator, square root of that is 9. To find the c value, I need to do a squared plus b squared. Just change the sign on whatever you see in the shape. So the two denominators are the 25 and 81. I will be adding those together to get c squared. So if I solve this equation, I'm going to have 106 equals c squared. And then we take the square root of both sides. But make sure you go through the effort of trying to reduce this radical. So in this one, it would break down as 53 times 2. And again, 53 won't reduce, so I can just leave my number as a square root of 106. But always try to break down that radical using your factor tree. See if there are any perfect squares that go into 106. That's another way of identifying it. So since I have all of my numbers, the center for this graph, it's not just the origin this time. Now I have the coordinate 1, negative 3. And then for my vertices, so I need to look at what A is, vertices or transverse axis tied to A. Since A came from the x coordinate, I'm going to keep, or the x variable, I'm going to keep adding and subtracting from the x coordinate. Now in this case, it's not just 0 plus or minus 5, so I am going to get different numbers. So I'm going to split this one up as a different coordinate. So both of the coordinates will have a y value of negative 3 because the y value is not changing here. So it's I'm just adding from the x's, so -3 and -3. So when I do 1 minus 5, that'll give me -4 for a coordinate. And then 1 plus 5 will give me 6 for the other coordinate. So if your center's not on the origin, don't just fall for the trap or the assumption that it's going to be plus or minus the same number. Actually compute out 1 minus 5 and 1 plus 5 to get those two different x coordinates. And then for my foci, I'm still going to be adding and subtracting from the x coordinate, but this time the number I'm adding is square root of 106. And since I wasn't able to reduce that, I'm going to be taking a whole number and a radical. Those are not like terms, so since I won't be able to combine them in any way, I'm just going to leave this as 1 plus or minus square root of 106, comma -3. You could still split it up as two different ordered pairs if you want, but in this case, that's an acceptable way to leave the answer since those are not like terms. And that's it for identifying the components.